We continue our discussion on MIMO channel capacity. In this particular lecture, we will look at the capacity of CMO and MISO channels as well as that of random channels. We will also see the situation when there is low SNR approximation and when there is high SNR approximation to see what happens to the MIMO channel. And that was going to give us insight into what has to be done when the channel SNR is low or when the channel SNR is high. So, with that, let us take a CMO channel. Let us consider a single input multiple output channel. So, single input multiple output, one antenna at the transmitter, multiple antennas at the receiver. So, basically it is a receive diversity kind of a situation. So, if you have this particular situation, your H vector is basically MR cross 1. So, if it is a single vector, so definitely the rank of this matrix is equal to 1, and we have a Frobenius norm of H is equal to sum of H I squared I equals to 1 to MR, and this is basically the lambda of the channel. So, this one could see as the lambda is basically eigenvalue of H Hermitian, which is basically this particular term. It does not have any other eigenvalue, and this is a rank 1 matrix. One can easily see because it is one column. Other ways are also there to prove that it is a one rank matrix. So, for a CMO channel, capacity of a single input multiple output channel, since there is only one data pipe, this is we have been saying the diversity mode is log base 2 1 plus ES 1 N naught times mod HF squared. So, mod HF squared is sum over all the channel gains. So, there is capacity increase, but definitely there is special there is only logarithmic capacity increase with MR. So, as MR increases, this increases. So, there is increase in the capacity over here, and that is it. So, basically there is only logarithmic increase in capacity, and even if you have channel state information at the transmitter, you can't do much because there is only one transmitting antenna. So, this is a single input multiple output case. So, when we go to multiple input single output scenario, in this case H vector is basically 1 cross MT, 1 cross MT, because you have H1 H2 in this format. In this case you would have H1 H2 up to HMR. This was the way we wrote MT. This is the particular notation, and again lambda 1, there is only one lambda, is Frobenius norm squared of H, and that is equal to sum over H I mod squared I equals to 1 to MT. So, here in case of multiple input single output, that means we have multiple transmit antennas going in this direction to a single antenna. So, if you do not have CSIT, that means no channel state information at the transmitter, you would put the covariance matrix of the signal as IMT, because you would have no specific direction. It would be sending them with equal power across all of them. In that case, what you are going to get is log base 2 1 plus ES by N naught. This will be the capacity of a MISO when there is no channel state information. See, if we compare these two terms, what we are going to get, because you are going to get HF squared, and again there will be ES by MT. So, they will balance out, whereas at the receiver there is no MT in the denominator. So, what we are going to get is what we could write is C MISO, no channel state information at the transmitter is less than or equal to max, you can get it in some case CMO, right. Whereas, if you have channel state information, if there is channel state information at the transmitter, then that means you have this case, you have S1 to SMT, but then there is something getting multiplied at some point, and there is one receive antenna. If you would remember, we had studied the dominant eigenmode, and we had also studied transmit MRC. and we said that this dominant eigenmode is basically one of the forms of transmit MRC along with MRC at the receiver. So, if we have this particular configuration, we can think of MRC or even as the dominant eigenmode transmission. In this case, we would have a capacity of a MISO system given as log base 2 1 plus ES by N naught times HF squared. So, what we see is with channel state information, because we would remember the capacity of or the expression of SNR for MRC at the transmitter or MRC at the receiver is basically this ES by N naught times HF squared, which gets reflected here also. So, with CS with channel state information, we can write this is equal to C CMO. So, this is just to remember that when you have single input multiple output, this is the expression of capacity. When you have multiple input single output, and when there is no channel state information, the capacity is similar to that of a CISO link. So, it is just like a CISO link, there is not much that you can do, but when there is channel state information in the transmitter, the capacity is same as that of a CMO link. So, this is something which we should remember. We move on now from this point to look at a random channel. We would remember that we have started with the channel condition which is deterministic, that means given a channel coefficient. So, now we would like to look at the case where this channel coefficients would be random, and what would be the meaning of that, what is the impact on capacity on when we look at it averaged over or over several such realizations of the channel. So, let us define that. So, we assume that elements of H, basically the Hij elements are normalized, so that expected value of Hij mod squared is equal to 1. So, that is the first normalization we look at, and we will use ES by N naught as the variable rho. So, the signal at the ith receive antenna is Yi is equal to root over ES by MT Hi S. Hi is the vector which is 1 cross MT, and see we are talking about the ith receive antenna. So, it is getting transmitted from all the antennas at the transmitter plus Ni, and we have to ensure that RSS trace of RSS is equal to MT. So, that there is total power of ES that is used. So, if we take E of Yi squared, we will get ES plus N naught. So, this is the average SNR at any one particular antenna, ES plus N naught. So, the average SNR is rho, which is ES upon N naught. Okay. So, next we move on further with this particular channel, and we say that H is basically HW, that means spatially white, and we also have MT equals to MR equals to M. So, when we have H as HW, MT equals to MR equals to M, we would have 1 upon M HW, this tends to IM as M tends to infinity. So, let us look at this, if this is true or why it is like this. So, if this is HW Hermitian. So, if we have 1 upon M, if I take a look at this particular expression, it is H11, H12 dot 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 H1C, I would write it, or I write H1M, H21, HM1, HMM times H11 star, H12 star up to H1M star, H21 star, like that up to HMM star. Okay. So, when we do this product, the big matrix that gets formed has elements 1 upon M, I equals to 1 to M, H 1 I times H 1 I conjugate, right, in the first one. The next one would be 1 upon M I or K equals to 1 to M H 1 M times H M 2, sorry, H this gets multiplied over here. So we have H2m, H1m gets multiplied by H12, sorry, HM2 conjugate, and so on. This particular element would be 1 upon m sum over H2i, if I put the index I, times multiplied by H1i conjugate. Okay. So this will be filled with such components where these diagonal elements would be sum over Hki or Hij mod squared, if you look at this 1 upon m, right. So this is what we are going to get, and finally it will be Hmi mod squared I equals to 1 to m 1 upon m, right. So that's the term that we are going to get. So as m tends to infinity, if we look at this first term, it is 1 upon m sum over Hik, any one of the terms, Hik squared, k equals to 1 to m, the ith row you can say, or the ith column. So as m is very, very large, as m grows, this is basically the mean value, and we have already stated that we would like E of Hij squared to be equals to 1. This is one of the constraints that we have put. That means on an average the channel, each channel link has average strength of 1. So due to law of large numbers, this one becomes, this can be approximated at the expectation of Hij mod squared, and which could be said being equal to 1. So all the diagonal elements would be equal to 1. If we take the non-diagonal elements, we are going to get 1 upon m sum over k equals to 1 to m Hik and Hjk conjugate for I not equals to j. So this would be equivalent to expectation of Hik Hjk conjugate, where I is not equal to j. So this particular term, because these are independent, that means we are taking a specially wide channel. So in that case, since these are all independent, this would turn out to be a 0. So because by law of large numbers we could write this as expectation. So what we have is all the off diagonal elements will turn out to be 0. So we had over here spatially wide. So basically H is equal to HW. So that means it's spatially wide. All are independent components. So if all are independent components, this term is equal to 0. So all the non-diagonal elements would be 0, and all the diagonal elements would be 1, including this particular term. So what this whole thing, so this particular product, what we started with, we can write 1 upon m HW Hermitian is equal to I of size m. So that means this again proves that this is orthogonal. So this is what we have. So using this, what we could write, the capacity C is equal to, we had sum of I equals 1 to m log base 2 1 plus Es upon m by n naught times H RSS H. So we had stated that we will put RSS to be identity matrix, and RSS trace of RSS is equal to MT. So that is what we had said, because there is no preferential direction of the channel. So in that case, this becomes identity matrix. So we have H Hermitian H, and this is HW. So 1 upon m times H Hermitian HW is also equal to identity. That is what we have shown over here in this particular expression. So what we have is basically sum of I equals to 1 to m log base 2 1 plus Es upon n naught. And if we see inside, there is no variable of I, so we could write this as m times log base 2 1 by 1 plus Es by n naught, and you could recognize this as the capacity of a seesaw link, and this is m times, right. So, what we see is when we have a spatially wide random MIMO channel and m grows very large, we have a linear increase in capacity over that of a seesaw link. So, if again we reach the same result. So, we are repeating the result several times. In a very general sense, we are saying that the capacity of seesaw is enhanced by linear increase of capacity. When it is an orthogonal channel, you achieve the same. When it is a spatially wide channel and m grows very large, the summations for 1 upon m h Hermitian HW Hermitian, the components become such that the diagonal elements are identity, whereas non-diagonal elements are 0. So, again that leads us to the situation where the capacity that we achieve is m times the capacity of a seesaw link, which is one of the most important gains that MIMO gives us, and because of which this particular topic has become so important for us. So, with this this particular message, we like to remember this particular message, and we would like to move on further. So, now what we would like to see is we have taken MIMO channel and we have taken random channel, but what we have seen is when m is very large is the particular expression that we have achieved. So, whereas if you look at C, given a value of h, it's dependent upon the h coefficients when m is not very large. So, basically C is dependent upon h and C is dependent upon lambda i's. So, for any given realization we have one value of C. Since h is random, basically h keeps on changing values, C would also keep on changing values. So, in that case how would we measure C is very critical. So, what we have is I will show you a particular graph. So, this particular figure shows us the distribution of capacity. Now, since we have seen that h is random, C is a function of h, definitely what we have is what we have over here is a distribution, because C itself is random. C is random, we have said. So, we have plotted the cumulative distribution function of C, and whenever we plot the cumulative distribution function, the curve would look, one of the typical curve would look like this. This is for the case where mt is equal to mr equals to 2 and SNR of 10 dB. Again, the reference is we have pointed out here. So, in this we have to note two important things. One is there is a 10 percentile point which is known as the outage capacity. That is very important. What it means is, from this, if I read this particular value as, let us say, 3.9 bits per second per hertz, what it means is that 90% of the time, this is 90% of the time the system provides a capacity value which is more than 3.9 bits per second per hertz. Along with this, there is also another important parameter, which is the ergodic capacity or the expected value of capacity, or basically C bar. So, this point is C bar, the average value of capacity. This particular point is the expected value of capacity, because we are getting, for each realization of channel we are getting a particular value of C. So, when I change the channel, because of time variability, we have studied these things in the early part. So, whenever channel changes because of time variability, we get a different value of C. So, if we collect a large number of C's, what we will see is that C is also a random variable. So, to characterize a random variable, we can do it by the CDF, or the cumulative distribution function, and two important numbers, if we have to take instead of the CDF, we can take the expected value, which is also known as the ergodic capacity, and we could also take the outage capacity, which we have just explained. So, moving further with this, when we look at the expression of C bar, that means it is the average value of capacity. It is basically expectation of sum over I equals 1 to R. So, we are taking a general channel, log base 2 1 plus Es upon mt times n naught, times lambda I, which is the eigenvalue of H Hermitian. So, this is without channel state information at the transmitter. Now, if there is channel state information, so with CSIT, with channel state information at the transmitter, we would write C bar as the expected value of I equals 1 to R sum over log base 2 1 plus S upon MT n naught times lambda I. However, there is a gamma I optimum, which we have seen how to arrive at in the previous lectures. What we will see is, again, when suppose we take the condition when SNR is high, when SNR is high. So, when we have a very high SNR, we could say that C is approximately equal to maximum. So, basically we are neglecting this, we will look at the other terms. So, sum of this is basically log of the product of this. So, log of product of this basically log determinant, which expression you are used to. You could write it is log 2 determinant of RSS times log base 2 determinant of ES upon MT times N naught times H. For especially white, we have HW Hermitian, and of course, it is maximized over trace of RSS being equal to M. So, when we look at this particular expression, that means we have taken for high SNR, this expression is maximized for a given HW is when RSS, when this is equal to identity matrix, right. So, when this is equal to identity matrix, what do we get? We get all the lambda i's, sorry. So, this is maximized for IM, that means when there is equal power on, if you have to maximize with respect to the power distribution across all these signal sources. So, and this comes from arithmetic mean geometric mean inequality. Again, we could go to that and we could show this. So, when we are saying that this is equal to IM, so this would in turn mean that we are putting equal power across all the branches. That means gamma i's are almost equal to each other, and that is also the case when there is no CSIT. So, what we are saying effectively is under high SNR and when H is equal to HW, when it is high SNR and H is equal to HW, we could say almost that C without channel state information at the transmitter is almost equal to channel without channel state information at the transmitter, the average the average channel capacity or the ergodic channel capacity. So, as M increases, we can say that the capacity gap between these two decreases, but with increase in SNR, when SNR is high, the capacity gap between these two decreases. That we will shortly see in one of the results. So, this particular result shows the ergodic capacity when channel is known at the transmitter. So, that is this solid line CSIT, and this is the ergodic capacity for no CSIT. So, there also we see as SNR increases, this gap between these two decreases, becomes better and better for higher values of SNR. Okay. We move further and we will see some more important results. Okay. We will derive some important results further, and we will give you some important analysis that is again very important. So, one approximation which we make is, one thing that we need to study is the low SNR regime. So, when SNR is low, so if we look at the expression of capacity, C is given by or the ergodic capacity is expectation of log base 2 determinant of I mr plus Es upon m T times n naught times H Hermitian. So, this is the expression. So, this in other words you could write it as log base 2 product of 1 plus Es upon m T n naught times lambda I equals to 1 to rank of H. So, we are taking the expectation, right. So, if we have to expand this particular product, we could write this, you could do it yourself, we are not doing it here exactly. You could get it as 1 as one of the terms, you would get sum over, you would get basically Es upon m T n naught. So, basically this when 1 gets multiplied with this, 1 gets multiplied with the second, and so on and so forth, you are going to get sum over lambda I equals 1 to rank of H, plus you are going to get Es upon m T by n naught squared times something plus 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 plus, and this is inside the log, and you are taking an expectation of that. So, again you could say it is expectation of log base 2. So, when Es by n naught is very small, these terms can be neglected and we are left with these terms. So, these terms would mean 1 plus, if you take a look at this, it is basically Es by m T n naught times the Frobenius norm squared of H approximately. So, in the low SNR regime, that means when SNR is low, these terms are all neglected. What we see is that the ergodic capacity is determined by the energy of the channel, which is indicated by this term, that means the total power. This gives us a hint that under low power or the low SNR conditions, what we need to look at is the Frobenius norm of H, and this Frobenius norm of H would give us what. So, this Frobenius norm of H, if you would see, was appearing in the error probability expression. So, when we had this error probability expression, there this Frobenius norm of H was being used in the exponent. So, we had H f squared to the power of m minus m, and so on and so forth. So, basically what this gives us a hint is when SNR is low, we have to strengthen this. The more we can strengthen this, more energy we can bring into the channel, the better it is. So, we would rather go for a diversity mode, is the hint that this particular expression is giving. We would like to stop this lecture at this point and move on with further discussion in the next lecture. Sorry.